We are going to move on to Jacob Jensen, one of our invited speakers, who will be talking about revealing core collapse supernovae and failed explosions with Roman, a topic dear to my heart. So I look forward to hearing this talk. Jacob, feel free to share when you are ready.
Okay, can you hear me?
And yes, and I will give you a 5-minute and a 2-minute warning.
Okay.
Yours is a bit longer.
And you can see the slides, all right?
Yep.
Okay. Thank you, everyone. I'm Jacob Jensen. I'm a postdoc at the University of Arizona and Stewart Observatory. So thank you again to the organizers for the invitation to talk. And like Ori said, I'm going to be talking about core collapse supernovae. And also probably spend a bit more time on what I've been doing more recently with failed supernovae that fail to launch successful explosions and may collapse into black holes, which I think are an exciting opportunity where Robin can have a pretty big impact. So, okay. Some of the work I did in my PhD was with a survey called SPIRIT, or the Spitzer Infrared Intensive Transient Survey, where we looked at a targeted search of nearby galaxies within about 20 megaparsecs between 2014 and the end of the Spitzer mission. So for about 5 years. And we basically found a whole host of different kinds of infrared transients, some of which weren't detectable in the optical at all with surveys that were running at a similar time. So you can see in this diagram here, everything that's a star is a transient that was detected by spirits or discovered by spirits rather than, in an optical survey that may have been running at the same time. And so I'll be focusing most of the talk today on the supernovae and also these failed explosions that I mentioned. But you can see there's a whole host of other things, mostly arising from massive star systems like luminous red novae that may be stellar mergers, and some of these things called sprites that we found, which didn't appear to have any optical emission associated with them whatsoever. So, the time domain in the infrared is a really exciting place to be doing things. And I think Roman will be, an exciting instrument to continue this. So this is just sort of a big collage of a lot of the greatest hits that we had from SPIRIT. So I'm not going to talk about most of these things in detail, but I just wanted to sort of show the diversity of objects that you can find when you have a good infrared transient survey. And I'll also refer you here to our ADS library, where you can find these and many other papers. And unfortunately, it's not a very easy link to remember. I don't know if there's a better way to reference it. But if the slides are available, hopefully you can track this down if you want to later. So the focus of the talk again is on core collapse. And so just a brief overview of why the infrared is so interesting to study specifically core collapse supernovae. So this image is a collage of basically all the detections of core collapse and in this case 1A supernovae from Spitzer that was put together near the end of the Spitzer mission by Thomas Salai. And you can also see compilations of SPIRIT supernovae from Gao-Tinianot. But this strong infrared emission that these core collapse events produce are interesting probes of the progenitor evolution and the mass loss leading up to the supernova, either through strong infrared emission produced by circumstellar interaction, or potentially in the case where you have circumstellar dust surrounding the star that reflects or absorbs and re-emits some of the light in a dust echo. Infrared emission is also important for telling us about how core collapse supernovae contribute to the enrichment of the ISM with molecules and dust, and also thereby galaxy evolution. And if you get into the polarimetry game, you can also learn about the explosion geometry of supernovae, which tells you about the explosion physics if there's any asymmetry. And the infrared is challenging but interesting because of the reduced degeneracies due to polarimetry that polarimetric signals that you can get from dust emission. So you can sort of break those degeneracies when you go into the IR. So sorry, I got a little tongue-tied there. So now after that short overview, I'm going to move into sort of the main topic of this talk, which is how can we build a complete census of massive star deaths? So we know that massive stars will end their lives in core collapse, potentially in a supernova explosion. And so I'm going to kind of break this down into two main sections. The first being, are we finding all of the core collapse supernovae, primarily when we look in the optical, or are there potentially missing ones? And then the second sort of separate question that will be most of the second part of the talk is whether or not all massive stars explode, or if some of them may collapse into black holes without this luminous supernova. So we'll move on to this topic first. I really only have one slide on this because I wanted to move into the failed supernova stuff, but the idea is that many core collapse supernovae, because they're associated with recent star formation and can be associated with these very dense, dusty regions of star formation, it's likely that many of them may be heavily obscured and thereby missed in the optical. And so a lot of the focus on this work has been looking in the dense nuclear regions of starburst galaxies and these luminous and ultraluminous infrared galaxies that are forming many, many stars and really dominate the star formation when you get out to higher redshifts in the universe, where basically all the supernovae are going off, but they're very, very hard to find. And so there's been attempts in the near infrared with HST or ground-based adaptive optics, in the radio with the VLBI, and then also if you stuck around for the poster pops, you saw Ori's poster on trying to do this in the mid-infrared with Spitzer of these LERGs and ULERGs. So I'll refer you to that poster as well to hear more about that. With spirits, again, we were targeting very normal galaxies in the local universe within about 20 megaparsecs. So these were sort of like normal star-forming spiral galaxies that you see pretty pictures of. And even in these normal galaxies, we found that there were many supernovae that were more heavily obscured than you might expect. And so in this histogram here, I'm comparing the results of spirits where you had supernovae, core collapse supernovae in the spirit sample that were detected in the optical as the gray bars. And then on top of that, additionally, the objects we found that didn't have an optical discovery and we discovered in the infrared with spirits. And you can see that, we really add to the high obscuration numbers here and sort of skew that histogram a bit more towards the high obscuration in comparison with a previous study that was done in the local volume looking at optically discovered supernovae. And so, a couple caveats here, the numbers are small. And some of these very obscured infrared objects, it was difficult to get confirming spectroscopy. In some cases, we had confirming radio observations. But some of the classifications here were a bit ambiguous. And so continuing to do this kind of work where you can get good confirmations and getting a much larger sample will definitely flesh out what these numbers really look like. But I think we can definitely say that even in these normal galaxies, there are lots of really red, very obscured things going off, some of which may be core collapse supernovae. And so there's a lot of interesting science to do in the infrared in the local universe. So now I'd like to move on to the second topic for the rest of the talk, which is this question of whether all massive stars actually explode as supernovae at the end of their lives. So the sort of, aspect we'll come at this from is this sort of large body of work over the last few decades that's been done trying to connect core collapse supernovae explosions to their progenitors. And so one of the main ways this is done is to look in high quality, high resolution, deep pre-explosion imaging that happens to exist for the galaxy in the region where the supernova went off. and try to pin down precisely the location where the supernova happened so that you can identify a progenitor star. So very often this is done with HST, although there are examples with ground-based facilities as well, especially when you have adaptive optics. And this is, one of the best examples of this. This supernova 2008 BK, which was a type 2. And you can clearly see this red star here in the pre-explosion image, which was precisely lined up with an image of the supernova. And then ideally in the aftermath, after the supernova fades, you can actually see that the star has disappeared, confirming that it was truly the progenitor. And so, like I said, a lot of this work has led to a pretty large compilation now. This is from 2015, although there's been several in the last few years that, have been added to this compilation of the progenitors of various types of supernova explosions and where they fall in an HR diagram. So, one of the biggest results of this was that the progenitors of type 2 supernovae, which are these hydrogen-rich, appear to be red supergiants here in black. But one of the surprising things was that when you look at the luminosities of these red supergiant progenitors, they didn't reach the luminosities that we think red supergiants should. So when you look, for example, at red supergiants in the galaxy, we find them up to higher luminosities, up to log L of about 5.5 or up to 5.8. And this is known as the Humphreys-Davidson limit. And so it was a bit surprising that as we built all of these supernova progenitors and built the sample, we weren't finding supernova progenitors up to this higher limit. Most of them appear to be lower luminosity and lower mass red supergiants. You can see here these other types of supernovae as well, the 2Bs, the 1Bs, as well as a 2N here. And most of these are probably the outcome of binary evolution, where you have some removal process for the envelope through interaction with a binary, which can change where the star appears in the HR diagram before it explodes. So like I said, this data from the type 2P progenitors favors an upper mass limit on whether a star actually produces a type 2 supernova of something like 16 to 23 solar masses, even though red supergiants are found up to about 30 solar masses. And so there's been a lot of work since Stephen Smart suggested this in 2009 and 2015. These are some of the papers which have gone back and forth debating the statistics of the sample, the methods by which you convert a luminosity from progenitor photometry into an initial mass. And so again, there's a lot of debate here, and whether this is truly a statistically significant result is still up for debate, but it's definitely an interesting question to look at as we build more and more supernovae with good progenitor detections. So on the theoretical side, there's also been a lot of work into trying to determine from the structure of the core at the time of collapse from stellar models and explosion models, whether the given star will explode or not. And there is appearing to be a similar emerging consensus that these stars that are more than about 20 solar masses may be more difficult to explode. But when you look at the distributions of the simulated stars that give these results here, from the low mass red supergiants up to more massive ones, you can see this sort of non-monotonic distribution in stars that might explode in green versus implode in black. And this is just one example of the kind of study that has done this. They don't look all exactly like this. But you can clearly see there's a lot of interesting physics that goes into these and determining the distribution from data of which stars will explode and which stars may collapse into black holes without launching an explosion will really tell us a lot about this final stages of evolution for massive stars. So one other thing before I move on to some of the observational work is that this process for forming black holes, where the star collapses and the core becomes a black hole and fails to launch a successful explosion, may still have associated transients. So the basic idea that has been proposed is that as the core collapses into a black hole and you lose all of this energy to neutrino radiation, these neutrinos also carry away mass from the core. And so that loss of mass in the center can produce a hydrodynamical response in the envelope, potentially producing a weak shock. So for example, the envelope of a red supergiant was simulated to see how it would respond to this loss of core mass. And it can produce this sort of faint, long-lived red transient, which you could see could last for a few hundred days here, associated with a failed supernova. So this is, one signature you could look for to try to find examples of failed supernovae. In a recent paper that was just out a couple weeks ago, I think, is looked through deeper stacks of archival IPTF and ZTF images. And they didn't find any transients that looked precisely like this. So they were able to put some limits on this kind of event. But certainly with the Rubin Observatory and Roman, will definitely have enhanced sensitivity to these kinds of things. So from the observational side, the sort of, smoking gun for a failed supernova would be if you could prove that a star like a red supergiant completely disappeared, indicating it had undergone core collapse and collapsed into a black hole without an associated supernova. So there's been a survey running now for more than a decade, led out of Ohio State with the Large Binocular Telescope, where they're surveying about 27 galaxies within 10 megaparsecs, where you can detect individual red supergiants from the ground. Currently they have one quite strong candidate, which looked like a red supergiant, and then in follow-up imaging, both with the LBT survey and in the optical and near infrared with Hubble, appears to have nearly completely disappeared, although there continues to be some faint and fading near infrared emission. So you can see some of the latest results on that. And they also put out a recent potential blue supergiant candidate, although this needs certainly further confirmation. So there, again, are only a handful of potential candidates. One was also published from an archival search with HST data, but again, would need follow-up and confirmation to prove that it really disappeared. And that one happened to look like a yellow supergiant before it faded. So now I'd like to come to the work I've been doing for the last few years in my postdoc, which is a new search for for failed supernovae with Hubble. So the basic idea of our search is that we observed a sample of 31 very prolific supernova producing galaxies with Hubble in 2019. So we got new images in the F814 filter, which is sort of similar to the ground-based I-band, which was chosen to sort of be optimally sensitive to red supergiants near the end of their lives. And so you can sort of see our search sensitivity here. Our new observations were deep enough to basically detect the disappearance of any red supergiant, and then the sort of shallowest archival images go down to detect basically any red supergiant above about 12, 15 solar masses. And so the sort of key to this project is, one, with the resolution and sensitivity of Hubble, you can go out further than from the ground. So we can observe more massive, more highly star-forming galaxies that are a little bit further away. And we also get extended time baselines with the HSC archives combined with the new data that we took. So, in some cases, for some of these galaxies, we have a time baseline to monitor red supergiants in excess of 15, 20 years. And so based on the sort of number of supernovae that have been found in this galaxy set, and have the appropriate amount of archival imaging that we could have detected the disappearance of a red supergiant, and then just sort of scaling with that supernova rate, we expect potentially 5, maybe even 10 in a very optimistic scenario, failed supernovae in this data set. So I'm going to take a little bit of time now to talk about our recent candidate, where I put out a paper a few months ago, which was in the nearby galaxy M51. So this is sort of the data we use to identify this candidate. You can see it was clearly detected in 2005 and 2016. So a long baseline establishing that this was a bright red appearing star, which appeared to disappear in 2019. And then this is our difference image where we identified it as a candidate. But we got some follow-up HST imaging, and in 2021, the star came back. And so this was very likely not a failed supernova, but still an interesting object that I'll give you a little more information on. So this is a full set of light curves. We had the most data in the sort of I band F814 filter, where you can see this sort of variable star, which had a small amount of variability going back about 26 years before this big fading event that we detected in 2019, and then the rebounding of the star in 2021. And so we did some SED modeling, and it basically looks like a very luminous, presumably massive red or yellow supergiant.
5 minutes.
Thanks, Ori. And so, this really was the type of object we were looking for. And this sort of points to a major difficulty in identifying true failed supernovae, is that we needed this follow-up imaging to really confirm that the star was gone. And in this case, it came back. And so this is definitely a potential contaminant in looking for these objects. So sort of interestingly, we recently heard a lot of this excitement about the great dimming of Betelgeuse, which is the nearest red supergiant to Earth. And so Betelgeuse, the data from the dimming event in this color magnitude diagram is shown here in purple compared to our object, as well as some other very luminous red variables in M51. So you can see, this is sort of the level of variability outside of the major dimming event, where unfortunately we didn't have any color information. But we were able to show that this was probably a relatively rare occurrence in the evolution of this star, or in the variability of this star, and was likely associated with some kind of episodic event rather than just part of its regular variability cycle. So it has some variability that looks similar to supergiant pulsations. And then when we compare it to what happened with Betelgeuse, where you have this sort of reddening of the light curve as it fades, which may have been associated with dust emission, with the formation of dust in front of the star that temporarily obscured it, which was potentially shown in some actually resolved imaging of Betelgeuse, which is very cool. But maybe this is kind of something that a lot of red supergiants do. So this is just another red variable star that I picked out from M51, which has sort of the same light curve morphology as this dimming event of Betelgeuse, and could have been something quite similar. So again, this is another topic that may be very exciting for a time domain survey with Roman, to have sensitivity to this kind of massive star variability and these dimming events that may also signify interesting instabilities in massive star evolution and mass loss, but are harder to study because they're not a bright transient that you can find in supernova search. So for the last few minutes, I'd like to bring it back to actually discussing failed supernovae and how we might find them with Roman. So of course, in the near infrared, you have the advantage that
Jacob.
Thanks. You're less hampered by extinction, whether that's foreground extinction, or if a star loses some mass, forms dust, and becomes redder towards the end of its life. So again, our HST search was really optimized for sort of like standard looking red supergiants, which are very bright in the optical I band. But if there was some evolution towards redder colors at the end of their lives, they may be difficult to find without a near infrared search. The other, of course, huge advantage of Roman is the large field of view. Here I'm showing 6946, just cut out from the MAST archive, where you can see there is basically a full mapping in WIF-C3 IR with HST, but that took 9 pointings compared to Roman that can get it in one shot. And there is a growing baseline of near infrared imaging with WIF-C3 IR, so more and more galaxies have some level of coverage. And so, that would provide an interesting baseline, potentially, 15, 20 years of several of these galaxies, for the first images that Roman could take of them. And so I also did a little calculation just looking at the 30 or so galaxies we used for the HST search, and sort of looking at their supernova rates and assuming we could get at least 2 images with Roman over 5 years. And we could find something like 3 to 6 failed supernovae. And if you actually include the coverage that those galaxies currently have with C3IR, so even if it's only 20% of the galaxy, there's still some chance you could find a failed supernova. Adding that all together, within 5 years of Roman, you could find 17 to 14 failed supernovae, and that's just in this set of 30 galaxies. So if you really looked at everything that's available in the HST archive, and really optimize the Roman survey, you could certainly up this number. So since I'm out of time, I'll just put up my summary and take any questions.
All right, thank you very much. Any questions? I see one from Lee. Thanks, Jacob. Would the much wider field of Roman lead you to select more nearby galaxies for such a survey, objects that are quote unquote too big for WIFC3?
Yes, that would definitely be something you could do. And I think a good advantage there is, they are so close, so you would get really excellent data. Comparing with the ground-based work that's been done for the LBT, probably for a lot of those galaxies. And so that would be one big advantage. I think though, even though it's a bit of overkill, you wouldn't want to leave out the sort of more massive and larger set of galaxies that are further away, because you have many more red supergiants in those galaxies. And so I think if you want to get the best rates, you will probably go out, a bit further to galaxies that are somewhat smaller than the Roman field of view. Does that answer your question? I don't know if you can answer.
I guess Lee can chat.
Okay.
But
yeah.
All right. Pat Morris asked, could M51 DSI fit a merger scenario with a large mass loss in the common envelope phase and dimming by fresh dust, and then destruction of that dust?
That's a very interesting idea. So thank you for the question. I guess in the paper, we didn't explore that in any detail. I think because, what sort of happened with Betelgeuse, this sort of dimming event from some sort of mass ejection, seemed like a plausible scenario. And I don't know, for example, if you could get away with that kind of merger scenario without having some kind of transient, especially in a massive system. The massive mergers or common envelope events we know about have very bright associated transients. So I would have expected to see something like that, but maybe when you have a supergiant involved, the scenario changes. I'm not 100% sure, but that's, a very interesting idea to look into.
Yeah, just to follow up, where was that on the HR diagram again?
I can go back to it. So it falls somewhere here. This is, including some level of foreground extinction, which we fit for in the SED fitting, whether that's foreground or circumstellar. And so there's sort of a range, but it's definitely, a massive supergiant.
But that green star indicates it could be a little bit more of a yellow supergiant than a red supergiant.
Yeah, correct. Yeah. Yeah, the X's here are just applying bolometric corrections to the near infrared data and assuming a red supergiant spectral type for various levels of extinction. And then the dots here and the star are the actual SED modeling where I fit stellar models, and the star is the best one. But.
That's interesting. Okay. Let's see, anything else? Did I miss anything? Pat does add Eta Car is probably a merger of supergiants.
Yeah, fair enough. So if you believe that, and there definitely was a transient in that case.
All right, well, you are out of time anyway, so that's great. Nice way to wrap up. Thank you very much.